Okay, I think we'll get started. So today we're going to talk about springs, talk about the forces associated with springs, and potential energy associated with the spring. So springs are one of the most important systems in physics, both the real spring and then an abstract idea of a spring. And so something that behaves spring-like is often used. And the next video we'll talk about simple harmonic motion, and that's the motion associated with the spring. So the next couple of videos here will get us going on this really important physical system. Now let's put it in context here in terms of sort of thinking about force here. So we've got Newton's second law, of course, F equals ma, and we might then ask ourselves, what are the situations for various forces? So we've learned about uniform motion already, and that occurs when there are no net forces on the system. So the system just, if it's moving at a constant velocity, then it just continues at that same velocity. We've learned about constant acceleration, and we did some examples with a charge near a charged surface, and the analogy is there with gravity as well. So something falling in gravity near the Earth's surface has a constant acceleration. Well, today with the spring forces, these are going to be linear in displacement. So if we move from equilibrium, the force will get bigger and bigger and bigger the farther we are from equilibrium. And it will be in the negative direction of that motion. So if I'm positioned at equilibrium and I move this way a little bit, I feel a restoring force, a force that wants to bring me back to equilibrium in this direction. If I go a little further, then I see a much bigger force in that direction. Likewise, if I move this way, a little bit, a little force, a lot, a big force. And so we call this a restorative force or spring-like force. And what kind of motion will this get? Well, uniform velocity, constant acceleration. This will give us oscillatory motion. So as I go this way, the force will want to accelerate me back this way. So I'll feel a deceleration. I'll stop. I'll start to accelerate back through. And then I'll come through my equilibrium, out the other side, and the same thing. So if I just follow this force, I would be oscillating back and forth. And so the spring forces are the source of oscillatory motion. Now, let's look at this a little bit more mathematically. The system that it's capturing in the most direct sense is a mass on a spring. There are two parameters in this system, the mass and the force constant, or the spring constant. So the spring constant is how stiff that spring is. So if we stretch the spring or compress the string, how much force per unit stretch does that spring have? Now, we can write this can be a little confusing, so we can write this as minus k delta x, right? So this delta x is interpreted as displacement from equilibrium. So if I'm here and I go here, I'm going to feel a particular restoring force. And that doesn't matter if I called this position 0 or if I called this position 10. If I step 1 unit over, now I'm at either position 1 in the first coordinate system or position 10 or 11 in the second coordinate system. What matters is this displacement from equilibrium. Now, we're often free to set up our coordinate system so that 0 is our equilibrium, in which case we can drop the delta and just write this as a function of displacement. Now, this is the more fundamental formula because it's displacement from equilibrium regardless of what the coordinate system is. This is if we set up in a nice coordinate system where the equilibrium position is 0. When the spring is shorter than its equilibrium length, then we call that compression. If it's longer than its equilibrium length, we call that elongation. And we can see the free body diagrams here. We can write a free body diagram for the mass at any position in its throw from fully compressed to fully elongated. And that free body diagram will change according to the position. Let's put this in graphical form. So F equals minus K X, if we're in, let's just stay in one dimension here. So we'll plot this position. The force then is a linear function, and the slope is K. In SI units, then that's newtons per meter. So the number of newtons it takes to either compress or elongate the spring by 1 meter. To get to potential energy, if we've had some calculus, we know that the potential energy is the integral of the force. So you can probably integrate this very quickly, and we get this. Now remember, the potential energy is a scalar function, not a vector, so it's independent of the direction. The force, of course, depends on direction and is a vector. So it turns out that the spring has a parabolic or a parabola potential energy function. All right, let's just do a couple of calculations to nail down these ideas. So let's imagine we hang a 1 kilogram mass on Earth, and then let's take that up to the space station where we'll say there's 0 gravity, and we see that the spring contracts contracts about 10 centimeters. And so what's happening is that here the free body diagram is the weight force, which is just m times g, and it's sitting at equilibrium, so the spring force is equal to the weight force. So that means it had to stretch enough, and as we stretch it, or the force gets bigger and bigger, it stretches enough such that it equals the weight force, equal but opposite. So the weight force is 9.8 newtons in the downward direction, and so I can take minus 9.8 equals minus K, and then the change in X is 10 centimeters. So we can write this as 9.8 over 0.1, or 10 newtons per meter. The K should always be a positive number. So if you get yourself mixed up a little bit with the vector directions, at the end, just always make sure that your K is a positive number if it's going to be a spring. All right, well, let's then say we took this to Mars. Mars has a different gravitational constant. It's much smaller than Earth's. So that means the mass wouldn't have to stretch the spring as much to equal the weight. The weight here is just going to be 3.73 newtons, because that's just 1 times this number. And again, it's downward, the force is upward, so the negatives will cancel, and we get X equals 0.038 meters, or 3.8 centimeters. All right, just to quickly finish here, you might wonder, well, what about linear, but not negative, positive? So this slope would be going this way. Well, that would be an unstable situation, because as I move, I feel a little force in this direction, so I move a little more and accelerate more and more and more and more. We won't really run into that situation, but you can think of it as maybe like a cart on a hill that's curving more and more steeply. So at first, if the cart is sitting right on the hill, it's in an unstable equilibrium. So a little perturbation one way or another, the cart will start to accelerate very slowly at first, and then that acceleration will grow and grow and grow as the hill starts to curve downward. And so that would be an example of a linear, could be an example of a linear with a positive slope. And that would not be restorative, that would be unstable. All right, so the next couple of lectures we're going to be talking about springs, and then we'll be able to utilize these to talk about molecules vibrating, at least in a classical spring-like analogy.